Hello and welcome to this new video. In this video, we will study one-step subgroup test and also we will see these two special sets are also the subgroup in any group. So we start with the lecture. Let G be a group and H is subset of G. Here we have written that H is subset of G. It is not clear that H is subgroup or not. So this is the question. We want to determine whether or not H is a subgroup of G. This is the question. So it is not possible every time to satisfy or to check all the axioms. So there is an important theorem which is called one-step subgroup test. Okay. The statement of the theorem is let G be a group and H is a non-empty subset of G. Okay. If A B inverse belongs to H whenever the elements A and B belongs to H, then H is a subgroup of G. Okay. We start the proof of this theorem. It means whenever we have to check that any subset is group or not, we have to check only this condition. Means whenever two elements A and B belongs to H, we have to check that A B inverse belongs to H. Okay. Given the operation of H is same as that of G, it is clear that this operation is associative. So one condition is trivial. The other three we have to prove. Next, we have to show that the identity element belongs to H. To show this, we know that since H is non-empty, so there must exist at least one element. We may pick some element that is X belongs to H. If we take A is equal to X and B also is equal to X, then according to this condition, A B inverse, which is actually equal to X, X inverse, because A is X and B is also X. and x inverse is identity, and this belongs to H. So identity element belongs to H. Now we move further. If we take, now we know that E belongs to H from previous statement. Now let A is equal to E and B is equal to X. X is any element in H. Then according to the definition or given axiom, that X E X inverse, which is actually equal to A B inverse, which is equal to X inverse, belongs to H. So this means inverse of every element of H also belongs to H. Now the last thing which we have to show that H is closed under the binary operation. So let take X and Y belongs to H. We have to show that the product of these two elements X and Y also belongs to H. Since inverse of every element belongs to H, this means Y inverse also belongs to H. If we take A is equal to X and B is equal to Y inverse, then according to the axioms, A B inverse, which is equal to X into Y inverse inverse, because B is actually Y inverse. So B inverse will be Y inverse inverse, and this is equal to XY, and this belongs to H according to the given axioms. Hence, H is closed with respect to the given binary operation, and all these concludes with H is a subgroup of G. Now, whenever we have a given set and we have to check that it is subgroup of G, then we have to check only the given axiom, or this is called one-step subgroup test. Okay, we consider an example. In that example, let G be any group. Of course, we considered abelian group. Abelian group means the commutative law holds with identity E, then the subset H of G, which is consists of those elements of G whose square is equal to identity element, is a subgroup of G. Now we have to show that whenever AB belongs to H, AB inverse belongs to H. This is what we want to show. Okay, consider A and B belongs to H. Since A and B belongs to H, and we know that those elements of G belongs to H whose square is the identity element. This means A square is equal to identity and B square is equal to identity. Now consider AB inverse square. If we succeed to show that AB inverse square is identity element, it means AB inverse also belongs to H, because H consists of all those elements of G whose square is identity. So AB inverse square means AB inverse into AB inverse. And since the associative law holds, so we can write it as, okay, since the group is abelian group, so A and this B inverse A can be written as A B inverse B inverse, and that is A square and B inverse square, and this can be written as a square and b square whole inverse. We know that a square is identity and b square is also identity. So e into e inverse, which is also e into e, which is e. So this means AB inverse square is also identity, so AB inverse belongs to H because H consists of all those elements of G whose square is identity. This means H is subgroup of G. This is what we want to show. Here we have another example. Let G be an abelian group with identity E, and let H be a subset of G consists of squares of all elements. We have to show, or we have to check whether this H is subgroup or not. We consider, or since E square, which is equal to again E, belongs to H. So identity must belong to H. This means this H is non-empty. Now consider those two elements, A square and B square belongs to H. What we have to show, we have to show that A square and B square inverse belongs to H. If we are able to show this, then according to the one-step subset test, H will be subgroup. One-step subgroup test. Okay. Consider A square B square inverse, which is equal to A square B inverse whole square, and that can be written as A into A B inverse into B inverse. And since the group is abelian, so this A B inverse can be written as B inverse A B inverse. And what is this? This is A B whole inverse square. So it means this element is also actually square of some other element. So this belongs to H. Hence, according to one-step subgroup test, H is a subgroup of G. So it is end of this video, and I hope this is an interesting video. Please subscribe the channel and like the video. See you next time.